The square root of 4, as I'm sure you know, is 2, a nice round whole number. However, when I ask my calculator what the square root of 2 is, it says 1.4141356 Well, that's as far as it can display on its screen, but this is actually a number which carries on forever, a decimal expansion which doesn't repeat. This is an example of what we call an irrational number, a number which cannot be written as a fraction. The proof that you cannot write the square root of 2 as a fraction of a whole number divided by another whole number is something that you'll need to know how to do later on in the course. For the moment, we are interested in expressions where we take the square root of a number and we do not get an integer. This is called a surd. So, for example, the square root of 2 is a surd. We also include rational multiples of these things, so 3 times the square root of 2 or 1/4 times the square root of 2 would all be considered surds as well. We begin with a couple of surd identities. Firstly, the square root of a times b is the same thing as the square root of a times the square root of b. This is quite easy to prove. If we took the square root of ab and we squared that, we would get the square root of ab times the square root of ab, which by definition is ab. If we took the square root of a times the square root of b and squared that, we would have square root of a times square root of b times square root of a times square root of b. But these are just 4 numbers, so we can multiply them in any order we want. If we put the 2 square root of a's at the beginning and the 2 square root of b's at the end, we will have root a times root a, which by definition is a, and root b, which by definition is b. So squaring both of these things gives us the same answer, and therefore we have that the square root of ab is the same thing as the square root of a times the square root of b. The other identity can be proved in a very similar way. Let us look at some examples which puts these ideas into practice. We're asked to simplify the following surds. What does it mean to simplify a surd? Well, in the first example, we're asked to simplify the surd root 12. What we need to do here is find the prime factorisation of 12. In other words, to split 12 into the prime numbers which make it up. 12 is 2 times 6, but 6 is 2 times 3, and all of these numbers are now prime. This is the prime factorisation of 12. Using the surd identity that we have just seen, we can write this as the square root of 2 times the square root of 2 times the square root of 3. But root 2 times root 2 is 2. So we can have 2 root 3 as a simpler expression for root 12, where we have written it in terms of a smaller surd. In part B, we are asked to simplify root 180. Now 180 is 2 times 90, and 90 is 2 times 45, and 45 is 3 times 15, and 15 is 3 times 5. So here is a prime factorisation of 180. We can now take the same idea and split this into root 2 times root 2 times root 3 times root 3 times root 5. But again, root 2 times root 2 is 2, root 3 times root 3 is 3, 2 times 3 is 6, so we have 6 root 5 as a simpler way of writing root 180. In part C, we're asked to simplify root 30. 30 is 2 times 15, 15 is 3 times 5, so 2 times 3 times 5 is a prime factorisation of 30. So we can split that up as root 2, root 3, root 5. However, this doesn't really look simpler than root 30. When we want a simplification of a surd, we'd like it written as just possibly a number out the front times a single surd, so 6 root 5 or 2 root 3. Root 2, root 3, root 5 isn't really particularly simple to look at. So although this is completely correct, we do not bother writing this as a simplification. We would not bother with this. We would say that root 30 is a simplified surd. Some more surds to simplify. In the first case, we have to simplify root 12 divided by 2. We've already worked out a simplified version of root 12, but let's just do it again to remind ourselves how that worked. 12 is 2 times 6, which in itself is 2 times 3. And then we can split the numerator up into root 2, root 2, root 3. Root 2 times root 2 is 2, so the numerator is 2 root 3. Denominator is still 2, and we can cancel those 2's, giving us just root 3. In part B, we have 3 terms to consider. Let's do them all separately. We have 2 root 180, subtract 3 root 20, plus root 245. So the first term will be 2 times, now what is a factorisation of 180? 2 90s, which is 2 45s, which is 3 15s, which is 3 5s. We've already seen this example, but it doesn't take a moment to do that again. The next term, 3 lots of root 20. 20 is 2 10s, 10 is 2 5s. The last term, 245. 245 is 5 times 49. 49 is 7 times 7. Now we can work on each of these pieces. The first one is 2 root 2, root 2, root 3, root 3, root 5. The second one is 3 root 2, root 2, root 5. The last one is root 5, root 7, root 7. And by now you should be looking out for pairs of identical surds which can be simplified as integers, such as root 2 is 2, root 3 is 3. So we have 2 times 2 times 3, which is 12. That's how many root 5s we have got in the first term. In the second term, we have 3 times root 2 times root 2. This part is 2, so 3 times 2 is 6. We are subtracting 6 root 5s. In the last term, the root 7 times the root 7 give us a 7. We have 7 root 5s. And so altogether, how many root 5s have we got? 12 subtract 6 plus 7. We have 13 root 5s. In part C, we have to expand some brackets. We have 3 subtract root 5 multiplied by 2 plus root 3. So doing our normal expansion of brackets, 3 times 2 is 6. 3 times root 3 is 3 root 3. Negative root 5 times 2 is subtract 2 root 5. And negative root 5 times root 3 is negative root 5 root 3. Can we simplify this? Just a tiny bit. We have 6. We cannot combine the 3 root 3 and the negative 2 root 5. They are about different things. But the root 5 root 3 would be much better written as a simplified surd of root 15. So a final answer would be 6 plus 3 root 3, subtract 2 root 5, subtract root 15.